Hey everyone, Thrasher here. In this video, we are looking at two types of mass, inertial mass and gravitational mass. We're going to look at what the differences are, where they come from, and what the point is, what this really is getting at. So first, inertial mass, part A. By Newton's second law, we know this. This is our classic F equals ma. The acceleration of an object is based on the net force acting on it divided by some property of that object, some property of this matter. Okay, how much this object accelerates is based on this inertia, this tendency that we've labeled as mass. This right here is inertial mass. We kind of said that inertia and mass are the same thing. When you think of inertia, think of mass. That's how we measure inertia, and vice versa. Okay, mass is the inertia, this fundamental property of material. Okay, we know things accelerate based on how much force and this property things have. That's inertial mass. Well, second slide, gravitational mass. We now have learned about the universal law of gravitation. And it says that the force of gravity is equal to some constant multiplied by some properties of these objects, some property of this matter, m1, m2, mass 1, mass 2, divided by the distance between them squared. The attractive force on matter is based on the distance, of course, all right, and their inertia, their mass. This right here is known as gravitational mass. The property that causes objects to feel this attractive force between them. Okay, so that's gravitational mass. Well, okay, we've already seen these two things, so you might be wondering, why am I making a video about it? These two equations are not based on one another. You do not derive this equation from this one, or vice versa. They are based entirely upon different investigations and different observations. All of us right now, if we had a force scale, okay, and we had a way to measure acceleration, we could look at an object, apply a force, measure its acceleration, and figure out the relevant mass associated with it. And maybe we can't do this easily, but it's possible, certainly not like in our homes probably, you don't have the right equipment. We can look at two masses, even though they'll be small, we could actually figure out how much force is acting on them if we had very precise scientific equipment. And of course, we can do this analysis for objects like planets and moons and stars, and using this force, we could make predictions based on velocity and the time to orbit, things like this. But they're very different. They do not come from one another. Okay, both of them rely on mass, this property. There's a property that affects the acceleration. There's a property that affects how much attraction there are between objects. Every experiment and every observation done in the history of science shows that these two masses, these m's, are the same thing. But there is absolutely no known physical reason why they have to be the same thing. Okay, let me say it again. Every time we've done an experiment, okay, if we take an object that's 1 kilogram, okay, and we apply a certain force, we get a certain acceleration that matches. Okay, if I then did a separate experiment with a 1 kilogram mass, if we measured force, we would get the expected values as if these were the exact same thing. When we make observations, we get the same values of mass no matter whether we're analyzing the object's acceleration or how much attractive force is acting on it. But there's no reason why this is true. To be honest, it's a bit of a mystery. Now, part D, my who cares. If you've ever heard of this guy called Einstein, he came up with a general theory of relativity. It's one of the most famous and one of the most used, especially in terms of modern physics and space travel, theories of our universe, theories of physics. And the theory is based upon almost entirely, it starts with the idea that these two masses, even though there's no real known reason why they should, are equivalent. Einstein starts with what's called the equivalence principle. That's what his entire general theory of relativity begins with. It's based upon. You could look this up here. You could Google equivalence principle. General relativity, in fact, could not be true, or at least it would mostly break down, if these two masses aren't the same thing. So then you might think, what if these masses, even though they certainly seem like they're identical, what if they're not? What if they are slightly different? What if in the quantum realm they are in fact slightly different? Again, there's no proof that says they have to be the same thing. There's no rule in physics that says this. All right, even modern physics is actually actively researching this. This isn't something that's just kind of a random thing we've all just accepted. There is research being done because maybe this will break down certain laws of science, or maybe this will help us unify certain rules of physics that are otherwise hitherto kind of separate from one another. In fact, Stanford, they do a research experiment where they are essentially checking to see if these masses are the same. Okay? Well, okay, let's kind of recap. The inertial mass, it's all about Newton's second law, this thing. Okay, you know you're talking about inertial mass when you're looking at forces and accelerations, these two things. Gravitational mass, well, of course, that's when we're dealing with gravity. When we use this equation, W equals mg, this here is the gravitational mass, obviously the universal law of gravitation, also using gravitational masses here. We've actually been assuming this equivalence since the beginning. Okay, when we set up, especially recently, Newton's law of universal gravitation, when we tried to solve for g, we crossed off these m's. This whole gravitational field strength assumes these masses are the same. When we would do it back in October, the sum of the forces, okay, these masses we always just assumed were the same value. There's nothing canceling here in this case. But if I just had an object in like free fall, well, the sum of the forces, that's just mg equals ma. Well, what's the acceleration? We assumed these two things were the same. That's how we could assume it was g equals 9.8 meters per second squared. Also, the whole idea of planets or moons or satellites orbiting is, again, presuming that these two masses are the same. But again, there's no real reason why they have to be the same. In fact, while we're certainly not going to get into general relativity in any real depth, again, this is the basic idea of his theory. What if all this stuff that we've since been discussing in terms of force, right? The Earth pulling down an apple, okay? A star pulling down on a planet. What if it's not really due to a force? What if it's really just simply this? The basic acceleration of an object, not due to a new force, but due to acceleration. This whole idea of these masses canceling, this g equaling m, this is the basis for where general theory starts off from and where it builds. And you can, of course, research that at your own leisure if you're interested. Okay, but I have seen the AP Physics 1 test. They will ask about these two different things. Now, you don't have to, like, all of a sudden rethink every question. Okay, but if they are very obviously mentioning inertial mass and gravitational mass, you have to recognize that there is a difference. Gravitational is when you're, well, using gravity. Inertial is all about the second law, when there's acceleration. You are expected to know which equations, or at least what relationships, if you are given, if it's obvious, which ones are including one or the other, whether that's a gravitational mass or an inertial mass. But again, all experiments say they are equivalent. Okay? That's it for my video. Thanks for watching.